Okay, I am BH Eric, and in my Z transform series, this is the lecture 1. Right, so in this lecture, the overview of this lecture would be: first we will talk about the discrete time Fourier transform and its convergence, and next we move on to the Z transform, and next we talk about the region of convergence of Z transform, and we will see a good number of examples to support the theory, and the last but not the least, you will take away the homework with you. Okay, right, let us start with discrete time Fourier transform. So for a discrete time signal x of n, the discrete time Fourier transform is defined as x of e power j omega equal to summation n equal to minus infinity to infinity x of n into e power minus j omega. Yeah. Okay, so this discrete time Fourier transform when a signal x of n will exist, or mathematically we say uniformly converges if and only if the given signal x of n is absolutely summable. That is, summation n equal to minus infinity to infinity modulus of x of n should be less than infinity. Right. So where do we use DTFT? We usually use DTFT to analyze the discrete frequency content of the signal x of n. Right. Now, if you look at the discrete time Fourier transform in LTA system perspective, so what is it we have seen in discrete time Fourier transform is that, so for an LTA system with impulse response h of n, its frequency response, which is denoted as h of e power j omega, they both form Fourier transform pair. That is, h of n will have h of e power j omega as the Fourier transform. So indirectly, what does this mean? We we see that because h often has discrete time Fourier transform, obviously the impulse response h often should be absolutely summable. So that is summation n equal to minus infinity to infinity modulus of h often should be less than infinity. But if you see the LTA system perspective, this condition actually tells that the given system with impulse response h of n is stable. So this is actually the condition for stability of the LTA system, or indirectly it means that the frequency response of the LTA system, which is nothing but its DTFT, will converge. So indirectly, what does it mean? Discrete time Fourier transform, as far as LTA systems are concerned, exists only for stable systems, right? So now the question may arise: why should we talk about another transform when we have DTFT? The answer is in the previous slide itself. So what does it say? The discrete time Fourier transform exists only for stable systems, right? So what happens? I have an LTA system which is unstable. So obviously, who will help us? The Z transform will help us. That is the reason why we have to talk about the Z transform of a system. So what will the Z transform will do? It may help us in analyzing a system which is unstable. So Fourier transform is like binary. So if the system is stable, we can have the frequency response. If the system is unstable, Fourier transform will not say anything about that. It says that system does not have frequency response. So but the transform will help us in analyzing those kind of systems which are unstable. So the transform will exist for both stable as well as unstable systems. So that perspective we will see in the coming lectures, but let us start with the definition of a Z transform. So for a discrete time signal x of n, the Z transform is defined as x of z equal to summation n equal to minus infinity to infinity x of n into z power minus n. So where z is some arbitrary complex number, and we can write it as r e power j omega. So if we substitute that in this equation, we'll get x of z equal to summation n equal to minus infinity to infinity x of n into r power minus n into e power minus j omega. And if you observe this equation a little bit carefully, you will see that this equation is nothing but the discrete time Fourier transform of x of n into r power minus n. So let us call that new signal as y of n and the corresponding DTFT to be y of e power j omega. So clearly, what is that we see? We see that x of z and y of e power j omega are same. So obviously y of e power j omega exists, or indirectly x of z exists if and only if the given signal y of n is absolutely summable. So what does it mean? The transform of x of n exists only if this equation is satisfied. So what is that? We require our signal y of n to be absolutely summable. So we will understand this concept with first example. Let us take our exam x of n to be a power n into u of n for some arbitrary real number a. So that is crucial. So in for this signal to have DTFT, my a should be my a should lie between 0 and 1. So to have the transform, you can have any value for a. So that is the crucial thing. Okay, so we'll talk about that later, but let us continue. So as the signal, as we have u of n in this signal, obviously it means that u of n is our unit step function. So obviously my x of n will start at n equal to 0 and ends at n equal to infinity. So it's the transform is given by substituting in our original equation, and we get x of z equal to summation n equal to 0 to infinity a power n into z power minus n. So if you expand that again by substituting z equal to r e power j omega, I will get this. So this is nothing but the DTFT of the signal a r power minus n, a r power minus 1 whole power n into u of n. Again with the same argument, this DTFT exists only if a r power minus 1 whole power n u of n converges. And if you look at this, it is clearly a geometric progression, and our signal, this we call it as y of n, will be of this form: 1 when n equal to 0, this will be 1 when n is equal to 1, this will be a r power minus 1, and so on. So clearly we have studied in our childhood days that this geometric progression converges only if the common ratio is less than 1. Absolute value of the common ratio is less than 1. So in this series, the common ratio is nothing but a r power minus 1. So obviously this series converges if and only if a r power minus 1 is less than 1. So if you simplify a little bit, you will see that we require r to be greater than mod a for absolute convergence, but we know that r is nothing but absolute value of z. So obviously we require that modulus of z should be greater than modulus of a for this signal, for this sequence to converge, or indirectly for this signal to have discrete time Fourier transform. So whatever we said, we again summarize here. We see that DTFT of a r power minus n u of n, or the transform of x of n, exists only if modulus of a modulus of z is greater than modulus of a. So this condition we call it as region of convergence. So what actually we mean by region of convergence, that is clear if you look at this geometric representation of this condition. So what does it say? Modulus of z is the circular radius of is a circle of radius a, and the region which is shaded. So in that region, the my z transform x of z will converge. Okay, here we have taken a to be greater than 1, and the mod z equal to 1, we call it as unit circle. We'll talk about that soon. Okay, right. So this shaded region we call it as region of convergence. So that's okay. But if what is the actual z transform signal? So if the we'll proceed. So if the region of convergence condition is satisfied, and by using this following fact which we have studied in discrete time Fourier transform, so for any signal with modulus of c less than 1, c power n u of n will have 1 by 1 minus t e power minus j omega as the discrete time Fourier transform. So here for a signal, for our signal y of n equal to a r power minus n u of n, we assume that the region of convergence condition is satisfied, that is mod z greater than mod a is satisfied. So obviously corresponding DTFT is nothing but 1 by 1 minus a r power minus 1 e power minus j omega, because c is a r power minus 1, but this is same as 1 minus a r e power minus j omega whole power minus 1, but we know that r e power j omega is z. So if you substitute this, you will get 1 by 1 minus a z inverse. Okay, but we know that y of e power j omega and x of z are same. So thus what is it we have seen finally? We have seen that the signal a power n u of n will have 1 by 1 minus a z inverse as the transform, and the corresponding region of convergence is modulus of z greater than modulus of a. Right, so now let us take one more example, which is nothing but x of n equal to minus a power n u of minus n minus 1. So clearly, because u of minus n minus 1 is there, this signal exists from minus infinity to minus 1. The corresponding the transform would be of this form. What is that? X of z equal to, because we have a minus sign here, so that we have put it out, and the signal exists from minus infinity to minus 1. Thus the summation will exist from minus infinity to minus 1 a power n into z power minus n. So if we expand this by keeping this minus out, when n is equal to minus 1, I'll get a inverse z. When n is equal to minus 2, I'll get a inverse z whole square, and so on. So this can be written as, by taking a inverse z out, minus a z in a inverse z into 1 plus a inverse z and plus a inverse z whole square, and so on. So again, if you look at this, this is like our geometric progression, and clearly this geometric progression converges only if absolute value of the common ratio is less than 1. So the common ratio for us is a inverse z. So this converges if and only if modulus of a inverse z is less than 1, or indirectly modulus of z should be less than mod a, and this is our region of convergence. So for the given signal, the region of, what is the given signal? A minus a power n u of minus 1 is a given signal. So for that, the region of convergence is modulus of z less than mod a. So clearly, if you look at in geometric way, so what happens? Our ROC is modulus of z less than mod a. So a is the radius of the circle, and this shaded region will give you the complete region of convergence. Again, here we have assumed that modulus of a is greater than 1. There is no rule that it should be always greater than 1. A can be even less than 1. So just for illustration purpose, we have taken a to be greater than 1. Right. Now, so again, because it is a geometric series, as we have already seen, and let us assume that the region of convergence condition is satisfied. So clearly, the z transform will converge to x of z equal to minus a inverse z by 1 minus a inverse z. So if you simplify this, this will become a inverse z by a inverse z minus 1. Right. So now if you multiply numerator and denominator with a z inverse, that is trivial stuff, so you'll get x of z to be equal to 1 by 1 minus a z inverse. So again, let us summarize this. What is it we have got? We have got minus a power n u of minus n minus 1 will have 1 by 1 minus a z inverse with ROC modulus of z less than modulus of a. So clearly you should have already seen why we have seen these two examples. Okay, right. So what is it we have observed from the previous two examples? So first example will say that a power n u of n will have 1 minus 1, sorry, a power n u of n will have 1 by 1 minus a z inverse with ROC mod z greater than mod a, and minus a power n u of minus n minus 1 will have same algebraic equation for the z transform, but where do they differ? They differ in region of convergence. So clearly, what is it we have seen? The both the signals. See, this signal a power n u of n will exist from 0 to infinity, which is completely different from another signal, which is minus a power n u of minus n minus 1, which exists from minus infinity to minus 1. So these two signals will have same z transform, but where do they differ? They differ in region of convergence. Thus, what is that you have seen in these two examples? We have, even though the algebraic expression of the z transform is defined, so that is not enough to define the complete z transform of a signal. So the algebraic expression as well as the region of convergence should be given to completely define the z transform of a signal x of n. Right. So again, let us take one more example. Let us take we will take some numerical value for a and see how does that replicate in our answers. Okay, so let us take x of n to be 1 by 2 power n u of n. So for this the transform, because this is like a power n u of n, corresponding the transform will be 1 by 1 minus a z inverse, where a is 1 by 2. So ROC clearly will be mod z greater than half. So geometrically it will look something like this. So look at this, I have a pole at z equal to half. So I hope that you know the definitions of zeros and poles of a transfer function. Okay, right. Sorry. Now let us take another example. X of n equal to minus of 1 by 2 power n u of n minus n minus 1. So again, with the example 2, we have seen that minus a power n u of minus n minus 1 will have again 1 by 1 minus a z inverse, where a is 1 by 2 as the transform, but clearly the region of convergence is modulus of z less than 1 by 2, right? So that is this shaded region. Again we have a pole at z equal to half, right? Now let us take one more example. Let us little bit complicated but not very much. Let us take a signal to be x of n equal to 2j by 3 whole power n u of n. So again this is looking like a power n u of n. So obviously the transform is not going to change. So now what happened to the ROC? ROC will be, if you have seen the example, we can see that modulus of z greater than modulus of a. But here a is 2j by 3. So if we take absolute value of that, it will become 2 by 3. But if you look at this, the algebraic expression of the z transform, we see that I have a pole at z equal to 2j by 3. So clearly it is the imaginary line of the z plane, and we have 1 0 at trivial 0 at z equal to 0. So that is visible in this graph. Along with that, we have a pole at z equal to 2j by 3. So again modulus of a equal to 2 by 3, the circle of radius 2 by 3. So clearly the region of convergence is this shaded region, right? So now let us take one more example, little bit typical. X of n equal to minus of minus 1 plus j by root 2 whole power n u of minus n minus 1. So we can write this. So just to confuse you, we have taken this, but this can be written as e power j 3 pi by 4 whole power n into u of minus n minus 1. Again, how is this looking? This is looking like minus a power n u of minus n minus 1. So corresponding the transform would be again 1 by 1 minus a z inverse, but ROC what will happen? Mod z less than mod a. You look at this a, so modulus of that is obviously 1. So that's why you'll get modulus of z equal to 1. So this, now if you look at this again, it has a 0 at trivial 0 at z equal to 0 and one pole at z equal to e power j 3 pi by 4. So that clearly will be of this form. So we have a pole here which is nothing but minus 1 by root 2 comma 1 by root 2. So but we have modulus of z less than 1. So this shaded region will become our region of convergence. Okay, now let us take one more example which is of this form. So we will take x of n to be 1 by 4 power n u of n plus 3j by 4 power n u of n. So for this we will split the z transform into two terms. So we will take the z transform, the first term, which is 1 by 4 power n u of n. Again with our previous knowledge, corresponding z transform would be 1 by 1 minus 1 by 4 z inverse with ROC mod z greater than 1 by 4. Similarly for second term, 3j by 4 whole power n u of n, the z transform would be 1 by 1 minus 3j by 4 z inverse with ROC mod z greater than 3 by 4. So why we have, because a is 3j by 4, modulus of a would be 3 by 4. So for overall z transform of x of n to exist, obviously what should happen? Both the region of convergence should be satisfied. That is, we want mod z greater than 1 by 4 and mod z greater than 3 by 4. So clearly when will both converge? Both will converge only if modulus of z is greater than 3 by 4. Right. So let us summarize that. So what is it? We have what? A 1 by 4 power n u of n plus 3j by 4 power n u of n will have 1 by 1 minus 1 by 4 z inverse with ROC mod z greater than 3 by 4 plus 1 by 1 minus 3j by 4 z inverse with mod z greater than 3 by 4. So overall ROC would be modulus of z greater than 3 by 4. So if you look at the geometric representation of this the transform, how does it look? So we have a pole at z equal to 1 by 4, which is the real pole, and hence we have a pole here, and z equal to, we have another pole at z equal to 3j by 4, which is an imaginary pole, so that will lie on the imaginary axis. So but what is ROC? Mod z greater than 3 by 4. So this whole shaded region would be our region of convergence, right? So we'll take one more example. So we'll take x of n to be minus 1 by 4 power n u of minus n minus 1 minus 3j by 4 whole power n u of minus n minus 1. So that transform again of the first term would be, with our again with the previous knowledge, we'll get 1 by 1 minus 1 by 4 z inverse, but now ROC will be modulus of z less than 1 by 4. Similarly for the second term, 3j by 4 minus 3j by 4 whole power n u of minus n minus 1, the z transform will be again 1 by 1 minus 3j by 4 z inverse, but with ROC mod z less than 3 by 4. So again, when will the z transform of x of n exist? Only if both the conditions are satisfied. That is, you want mod z less than 1 by 4 as well as mod z less than 3 by 4. Clearly, when will both converge? Both will converge only if modulus of z is less than 1 by 4. So clearly, again we will rewrite the final result. So what do we get? Minus this whole signal will have this as the z transform. So with overall ROC, which is nothing but modulus of z less than 1 by 4. So if you look at in a geometric plane, so it will look something like this. So we have a pole at z equal to 1 by 4, and we have a pole at z equal to 3j by 4, and we have got the ROC to be mod z less than 1 by 4, which is nothing but our this shaded region. Okay, now let us take one more example. So I have x of n to be 1 by 4 power n u of n minus 3j by 4 power n u of minus n minus 1. So again, with our previous knowledge, corresponding first term for z transform would be 1 by 1 minus 1 by 4 z inverse with ROC mod z greater than 1 by 4, because we have this as a power n, because this is looking like a power n u of n, ROC would be mod z greater than 1 by 4. Similarly, this flow is looking like minus a power n u of minus n minus 1. So obviously the transform would be 1 by 1 minus a z inverse with ROC mod z less than mod a, which is nothing but 3 by 4. So when will both converge? So the transform of x of n to exist, both the algebraic terms should converge. This is possible only if the region of convergence lies between 1 by 4 and 3 by 4. So clearly this signal will have 1 by 1 minus 1 by 4 z inverse plus 1 by 1 minus 3j by 4 z inverse with the corresponding ROC 1 by 4 less than mod z less than 3 by 4. So if you look at this geometrically, you will see that it is a ring which is bounded by the poles 1 by 4 and 3j by 4. So clearly, if we look at this carefully, there are two zeros at trivial zeros at z equal to 0 because of this. Okay, right. Now let us take one more example, which is nothing but x of n equal to minus 1 by 4 power n u of minus n minus 1 plus 3j by 4 power n u of n. If we look at this again, this is trivial. These are easy steps. I don't say trivial. They are easy to find out. So that this signal will have this as a transform with ROC this one, and this signal will have this as a transform with ROC this one. So obviously, when will the transform exist for both the guys? The transform will exist for both the guys only if both converge. That is, we want mod z to be less than 1 by 4 and mod z greater than 3 by 4, which is impossible. So and hence for the given signal does not have the z transform. So again, for last four examples, let us summarize. So this signal and this signal will have same z transforms, but look at them carefully. Even though they have same z transform, they differ in ROCs. So and hence again these three examples will reiterate that what for a given z transform of a discrete time signal, ROC is a must. Okay, so just so those are that is the beginning lecture of the transform. So if you are interested, you can take this as a homework and give a try. So inverse Z transform actually we did not see, but it is always good that if you, it is always good if you can try it. Okay, thanks.